At its most basic, a Bernoulli trial is a trial that only has two possible outcomes. Okay, now we call these, in all circumstances, we call them success or failure. We'll talk more about that later on. But for example, if you toss a coin, there's only two possible outcomes. That's tails or heads. Okay, if you talk about your arrival at school, you're either late or you're on time. Okay, so there's many different areas that can have trials that involve only two outcomes, and if they only contain two outcomes, then they are known as Bernoulli trials. Okay, now where do Bernoulli trials come in with probability? Well, we can use Bernoulli trials in calculating probabilities of an event or given events, as long as we take into consideration other scenarios. Okay, so there are other conditions that have to be present in order to use Bernoulli trials in calculating probabilities, and we'll talk more about those in a moment. So just at its most basic, a Bernoulli trial is one that has two outcomes. All right, now to expand that a little bit, if there's only two outcomes, then each of those two outcomes, success and failure, have their own individual probabilities. However, the sum of their probabilities will always be 1. Okay, so let's just take an example. Let's just dive straight into this, because the examples make it a little bit easier to understand. There are 300 girls and 100 boys in a school. Now, when they give you something like that, you take that as being 400 students. Okay, that's the whole school body. Each weekday, the principal randomly chooses one pupil to read the school announcements. Find the probability that the principal chooses a girl exactly 3 times and a boy exactly twice. Now, is this a Bernoulli trial? Well, how many outcomes are there when the principal chooses? There's only 2. It's either a boy or a girl. So the first thing we've got to do is to work out the probability of a girl and work out the probability of a boy being chosen. The probability of a girl being chosen is 300 over 400, which is 3/4. And the probability of a boy being chosen is 100 out of 400, which is 1/4. Okay, now what does she want to select? The principal chooses a girl exactly 3 times and a boy exactly twice. So therefore, at its most basic, it could be Monday, Tuesday, Wednesday, Thursday, Friday. So she might have a girl, a girl, a girl, a boy, a boy. Okay, a girl and a girl and a girl and a boy and a boy. So at its most basic, it's going to be 3/4 by 3/4 by 3/4 by 1/4 by 1/4. Okay, now we don't like to repeat ourselves in maths. We like shorthand ways to write things down. So that's the same as 3/4 raised to the power of 3, 1/4 raised to the power of 2. However, this has to be a random selection. So there's no rules on who reads when. So therefore, only one possible scenario or one possible combination is girl, 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 boy, boy. There are other combinations, perhaps girl, boy, girl, boy, girl. Or perhaps the boys are at the ends and the girls are in the middle, or all over the place. Okay, we don't know. But there are other combinations of boys and girls. Now, in a situation like this, we have to decide which of these two possible outcomes are going to be the success and which one's going to be the failure. Not that choosing a girl is a success and choosing a boy is a failure. Not that type of success and failure. Success and failure simply means when you choose what you're focusing on, that's a success. But if you choose what you're not focusing on, that's a failure. Okay, more about that in a minute. So in that case, how many days do we have? 5. How many girls are to be selected? 3. Or you could say, how many days have we? 5. How many boys to be selected? 2. So either way, this is only one of a possible number of combinations. So how many combinations are there? Well, 5 days, choose any 3 girls. Or you might say, 5 days, choose any 2 boys. But I hope you notice they're exactly the same. 5C3 and 5C2 happen to be the same thing because, as I told you before, you can simplify a combination. Look at the bottom term. If the bottom term is greater than half the top one, take it away and simplify your combination. So what I'm going to do down here is I'm going to place 5C2 in front of these two 3/4 to the power of 3 and 1/4 to the power of 2. I hope you recognize that, because in the very early chapters of book 1, back at the beginning of 5th year, we talked about the binomial expansion. Okay, and when we were dealing with the binomial expansion, we were also dealing with Pascal's triangle. And whatever layer of Pascal's triangle we were on, we had certain numbers, and those numbers were calculated using NCR. Okay, but not only that, when we wanted to get an individual term from a given binomial expansion, we used this particular formula here. So this is the formula that also allows me to write out one term in a given binomial expansion. So just as an aside, a Bernoulli trial can also be called a binomial distribution. Okay, so just watch for the two names. They are interchangeable. So what does this work out as? Well, 5c2 is 5 by 4 over 1 by 2. That's 20 over 2, which is 10. 3/4 to the power of 3, that's easy. It's 27 over 64, not in your head. And then we've got a quarter squared, which is a 16th. And when we multiply those three together, we get 135 over 512, which is in decimal form 0.2636. Okay, now let me just remove that and I'll show you the way in which I have this typed out. So again, two outcomes, boy, girl. What's the probability of girl? What's the probability of boy? Who's going to be my success? Who's going to be my failure? You choose that yourselves. Okay, if 5 days have to be filled with 3 girls and 2 boys, the most basic combination would be girl, 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 boy, boy. But there are other combinations. The order is not important, so therefore it's not a permutation, it's a combination. Okay, order is not important, so we've got to figure out how many ways can I get 3 girls to read over the 5 days, 5c3, or how many ways can I get 2 boys to read over the 5 days? Exactly the same thing, but that has to be placed in front. So when we put that in front, 5c3 becomes 10. 10 times 3/4 to the power of 3 times 1/4 to the power of 2 is 0.2637. Now, what did we notice about that question? Well, first of all, we noticed that a pupil was selected randomly. So there's no rules in how these people are selected. Okay, and that's key. Randomness has to be a part of this, and we said that from the very beginning of probability. Number 2, the experiment was repeated 5 times, 5 days, Monday, Tuesday, Wednesday, Thursday, Friday. So there was repetition of the event. Okay, there were only 2 possible outcomes, boy or girl. The probability of selecting a boy and a girl was the same for each day. So therefore it was 3/4 to 1/4 on Monday, and on Tuesday, and on Wednesday, and on Thursday, and on Friday. Nothing changed. So the probabilities didn't change. And lastly then, when these 4 conditions are present, then the trial is noted as a Bernoulli trial, and we can use probability calculations with the Bernoulli trial to work out a whole plethora of probabilities in terms of one event or a number of events, providing that the events or the trials themselves are Bernoulli in nature. Okay, so more generally then, a Bernoulli trial is an experiment that satisfies 4 conditions. Number 1, the experiment is repeated n times. Okay. Number 2, there are only 2 possible outcomes, success or failure. Now success is what we're focusing on. Just keep that in mind. Okay, success is what we focus on, failure is what we're not focusing on. It's not the literal translation of success and failure. Hooray, I chose and oh I didn't. Yeah, no, it's success or failure as in I chose what I'm focusing on or I chose what I wasn't focusing on. Okay. Thirdly, the trials are independent. Now what that means is that the probability of the first event doesn't interfere with the probability of the second one. And therefore, we've got, in the case with the boy and the girl, 3/4 to 1/4, and that remains constant right the way through, which is the 4th condition. In this situation, we're going to let P equal the probability of success. So in other words, what you've decided to be the success, when you work out the probability of success, that's P. Q therefore will be the probability of failure. But because there's only 2 outcomes, the probability of success plus the probability of failure has to be equal to 1, because 1 is the highest probability we actually have. Okay. P, the probability of R successes then, uses the formula NCR multiplied by P to the power of R, Q to the power of N minus R. What does that mean? N is the number of trials. Okay. R is the number of successes. P is the probability of success. R is again the number of successes, same as down here. Q is the probability of failure. Okay, and N minus R is the number of failures. So that's what N minus R stands for. So everything in here has a value. Okay, N is the number of trials, R is the number of successes, P is the probability of success, Q is the probability of failure, and N minus R is the number of failures. And when we use them together in that formula, we can work out the probability of having a certain number of successes. So you may notice, as I told you before, that the Bernoulli trial uses the same formula as the binomial expansion. So therefore a Bernoulli trial can also be called a binomial distribution. Okay, so how do we work out these questions? Once I establish a question is an actual Bernoulli trial, how do I work it out? Well, first of all, write down how many times the particular trial is repeated. That's n. Then choose which one of the two outcomes is going to be your success and your failure and work out their probabilities. Thirdly, work out how many successes do I want. Okay, let that be R, and then use your formula, which we said already is NCR multiplied by P to the power of R, Q to the power of N minus R, better known as number of trials, C number of successes, multiplied by the probability of success to the number of successes, multiplied by the probability of failure raised to the number of failures. Okay, quick question. A fair coin is flipped 8 times. Find the probability that a tails comes up exactly 4 times, or exactly 7 times, or in the third part, 7 or more times. So let's do part 1. First of all, is this a Bernoulli trial? How many outcomes are possible when you flip a coin? Only 2. If there's anybody out there who's managed to get the coin to stand on its edge after flipping it, let me know. I'll be your manager. We're going to earn money. Doesn't happen. Okay? Flip a coin, heads or tails. Simple as that. So are there 2 outcomes? Yes. So there's 2 outcomes. How many times do we repeat the experiment? 8. So therefore, all of a sudden, n is equal to 8. Now, what do we want? What are we focusing on? Tails. So therefore, tails will be my successes. So what's the probability of a tails? The probability of a tails, or the probability of success, is a half. What's the probability of a heads? It's going to be a half as well. So therefore, we're going to call this our success. So P equals a half, Q equals a half, and N is equal to 8. Okay, in part 1, how many successes do I want? I want 4 successes. I want 4 tails. So what that means is, out of the 8 repeated experiments, I want 4 successes. The probability of success is a half raised to the power of 4, and the probability of failure is a half raised to the power of 4. So 8C4, I'll do this very quickly here, 8C4, and that's equal to 70. So 8C4 is 70, multiplied by, well, 2 to the power of 4 is 16, 1 over 16, and again 1 over 16. So therefore 70 multiplied by 1 over 16 multiplied by again 1 over 16, and that comes out, the trusty calculator, as 35 over 128. So that's the first one. Exactly 7 times. Part 2, exactly 7 times. Okay, how many times did I repeat the experiment? 8. How many successes do I want? 7. How many failures am I allowed? 1. So what's the probability of success? A half. So if that's success, there are 7 successes. Probability of failure is a half, and I want 1 failure. So again, the same thing. Now, 8C7, I hope you remember, is 8C1, okay, which is 8. A half to the power of 7, well, 2 to the power of 7, let's see what the denominator becomes, and that's 128. And then a half is 1 over 2. So therefore, 1 over 128 multiplied by a half multiplied by 8, and that comes out as 1 over 32. So that's the probability of that one. And then the last part, 7 or more times. Now let me just clear this, because 7 or more times means that you can get 7 or 8. So 7 or 8 successes. Okay, so what's the probability of 7 successes? Well, that's 8C7. We've already had that in the previous part. 8C7, a half to the power of 7, a half to the power of 1. Okay, what about 8 successes? 8C8 by a half, which is success to 8 successes, and a half to no failures. See that? So because it's the word or, we're going to add those together. So again, that's 1 over 32, if I remember from the previous part. I think it is 1 over 32. And then this one here, 8C8, well, 8C8 is the same as 8C0, which is 1. So that's 1. A half to the power of 0 is 1. So 1 and 1, that's multiplied by 2 to the power of 8. And 2 to the power of 8 is 256. So therefore it becomes 1 over 32 plus 1 over 256. So 1 over 32, and you add on to that 1 over 256, and the answer there comes out as 9 over 256. And that's it. Okay, so just watch the language. The word or means add, the word and means multiply. Pick what your success is, pick what your failure is, and assign their probabilities. Then use the Bernoulli or the binomial distribution. Okay, so again, that's done for you. So you can look at that yourselves. And the same answers we had there a moment ago. 1 over 32 plus 1 over 56, 256, which is 9 over 256. Okay, I'm going to take 3 examples from using the binomial distribution or Bernoulli trial easily, and then I'm going to go on to a further 3 examples which have a little complication in relation to the way in which we have to look at the combinations of outcomes. Okay, in Ireland, 40% of the cars are Japanese. 10 cars pass a point in Ireland randomly. What is the probability that exactly 4 are Japanese, correct to 2 decimal places? Now, is this a Bernoulli trial? What are the outcomes? The outcomes are it's a Japanese car or it's not a Japanese car. Okay, so you've got the probability of being a Japanese car and you've got the probability of not being a Japanese car. So what are we told? 40% of the cars are Japanese. So the probability of Japanese is 0.4, meaning that the probability of not being Japanese is 0.6. Now, which one of these two is going to be my success? Well, the question is asking me about the probability that the 4 are Japanese. So that's going to be my success and that's going to be my failure. So that means P is equal to 0.4 and Q is equal to 0.6, because we always allow the success to be P and the failure to be Q. Okay. How many times has this experiment been repeated? Well, 10 cars pass a point. So that's N equals 10. And from that, what are we asked to do? We want to find out that exactly 4 are Japanese. So R is equal to 4. That's the number of successes I require. So probability of success, probability of failure, number of repetitions of the experiment, and there's the number of successes I require. So how do I get the answer to this? Use the binomial distribution of the Bernoulli trial. It becomes 10 C4. What's the probability of success? 0.4 raised to the power of 4 by 0.6 raised to the power of 6. Because don't forget, both of these have to add to 10. Okay, so 10C4 multiplied by the probability of success raised to the number of successes multiplied by the probability of failure raised to the number of failures. Now 10C4, so again, just let me work this out quickly. 10C4, and that comes out as 210, multiplied by 0.4 raised to the power of 4 is 16 over 625. And I always tell you, make sure work with fractions rather than decimals. Give your answer back in decimals, but work with fractions in this case. And 0.6 raised to the power of 6 is equal to 729. These are unusual fractions. 15,625. Okay. Now let's multiply them out. So multiply that by 16 over 625, and then in turn multiply that by 210, and the probability comes out as 0.2508. And I would normally take 4 numbers after the decimal point just to be a little bit more concise than 2 numbers. So 0.2508, that's it. Oh yeah, but corrected 2 decimal places, that's what it says there. So 0.25. You've got to give back what the question asks. Okay, next one. A student is doing a multiple choice test. Only one answer of the 4 possible answers in each question is correct. The student answers 5 questions using guesswork alone. What is the probability to 2 significant figures of getting 3 or more correct? Now again, start at the beginning. Is this a binomial distribution? Is this a Bernoulli trial? Well, first of all, what are the 2 outcomes? The 2 outcomes are correct or incorrect. So therefore you've got the possibility of correct and you've got the possibility of incorrect. Okay, now what does it say? One answer out of 4 possible answers is correct. So that's 0.25. That's a quarter. So that must mean then that this being incorrect is 0.75. The student answers 5 questions using guesswork. What is the probability of getting 3 or more correct? So therefore my success criteria is correct. So that's going to be P equals 0.25, Q equals 0.75. Okay, how many questions? The student answers 5 questions. So n is equal to 5. And how many correct do I want? What's the probability of getting 3 or more? Now, that's 3 or 4 or 5. Okay? Now, you can do this in one of 2 ways. You could work out the probability of getting 3 correct, then 4 correct, then 5 correct, and add them together. Or you could also have, if you wanted to, 1 minus the probability of getting none, 1, or 2 correct. Now, that's up to you, whatever you want to decide yourself. I'm just going to stick with what's here. Okay? So, what is the probability to 2 significant figures of getting 3 or more correct? So, here's what we've got to do. Let's work out the probability of 3 correct first of all. 5 questions, I want 3 correct. The probability of getting them correct is 0.25. Number of correct, 3. Probability of failure or incorrect, 0.75. Number of incorrect, 2. Or, that's and, 5C4 by 0.25 to the power of 4 by 0.75 to the power of 1, or 5C5 by 0.25 to the power of 5, 0.75 to the power of 0. Okay, so once you begin to use this thing quite frequently, it does become quite easy. 5C3, which is the same as 5C2, is 5 4s or 20 over 2 is 10. 0.25 raised to the power of 3 is equal to 1 over 64, or let's use decimals this time, 0.0156. Okay, multiplied by 0.75 raised to the power of 2, and that becomes 0.563. Okay, plus 5C4, well, that's exactly the same as 5C1, which is 5. 0.25 raised to the power of 4 comes out as 0.0039 multiplied by 0.75, plus 5C5 is 1. 0.75, that's 1. So that's going to become 1, that's going to become 1, so don't worry about them. So it's just 0.25 raised to the power of 5, which comes out as 0.000977. Okay, so let's work out each of these. First one, 10 times 0.0156 times 0.563. So that comes out as 0.0878. 5 times 0.0039 times 0.75, and that comes out as 0.0146, and lastly 0.000977. So 0.000977 plus 0.0878, and if you add those three together, let's see, 0.0878 plus 0.0146 plus 0.000977, and that comes out as 0.103. Corrected 2 significant figures, that means you keep these 2 and drop that. Answer 0.10. Okay. Next one. When a certain drug is used, there is a 5% chance that the side effects will be suffered. 20 people are given the drug. Find to the nearest percent the probability that none will suffer side effects. Now, none will suffer side effects. Okay, so what does that mean? First of all, is this a binomial distribution? Is this a Bernoulli trial? Yes, it is. Why? Because the 2 outcomes are either side effects or no side effect. Okay, so the first thing we establish is, what's the probability of a side effect? Well, the probability of a side effect is equal to 5%, which is 0.05. The probability of no side effect, therefore, is 0.95. All right, so therefore we're going to allow this one here, because it's asking me none will suffer side effects. So therefore that's going to be P. So P is 0.05 and Q is 0.95. So that's my success and that's my failure. Okay, what are we told? 20 people are given the drug. So in this case here, N is equal to 20. What's the probability that none will suffer side effects? So I don't want any side effects. I don't want any successes, so to speak. okay, because the side effect is a success. We don't want any successes, so R is 0. So what's the first answer? 20 C0 by 0.05 to the power of 0 by 0.95 to the power of 20. So therefore 20 C0 is 1. Anything to the power of 0 is also 1. So therefore we have 0.95 raised to the power of 20, which is 0.3584. So there's part 1. Part 2. More than 1 will suffer side effects. Now that's huge, because that could be 2 or 3 or 4 or 5 or 6. But instead of going that way, can you see another way to answer this? More than 1 would mean not none and not 1. So therefore it's 1 minus the probability of none or 1. See that? So it's a much easier way to calculate the whole thing. Now you could of course go along and you could do 2 or 3 or 4 up as far as 20, but you'll be there all till Christmas, okay? So you'll probably outlast the coronavirus. But at this stage, we take it easy. More than 1 means not none and not 1. So let's work that out. So what's the probability of not having any? Well, we know that already. It's 0.3584. So we already know it's 1 minus 0.3584. Or what's the probability of 1? Now we have to work that out. So out of 20 patients, 1 success, 1 shows a side effect, in other words. Yeah, 0.05, which is the probability of success to the power of 1, by 0.95 to the power of 19. So let's work that out. 20C1 is 20. 0.05 power of 1, 0.05, and 0.95 raised to the power of 19. 0.95 raised to the power of 19 is 0.3773. Okay, so therefore multiply that by 0.05 and then again by 20, and that comes out this time as 0.3774. Okay, so 3774. Now 1 minus, don't forget, so add on to that 0.3584, and that becomes 1 minus 0.7358. Okay, just to round it off. So 1 minus that comes out as 0.2642. So that's the answer to part 2. Now again, look at what I did. More than 1 will suffer side effects. There's too many to worry about, because there's 2 or 3 or 4 or 5 or 6 or 7 up as far as 20. So instead of that we say not none and not 1. So it's 1 minus the probability of none or 1. And that's what I did here. We know the probability of none is the first answer, 0.3584. The probability of 1 I've just worked out down here as 0.3774. So I add these two together, take it away from 1, and that's the probability that more than 1 will suffer side effects. Okay, part 3. The company that produced the drug claims when 20 people are tested at random, there is a less than 8% chance that 3 or more will suffer side effects. Is this claim true? Now, 3 or more, what does that mean? 3 or 4 or 5 up as far as 20. We don't want to go down that route. So instead of going 3 or more, it's going to be 1 minus the probability of none or 1 or 2. Okay, now you don't bother with 3 because 3 or more is what we want to look at. So in that case there, we're talking about the probability of 3 or more is the same as saying 1 minus the probability that none have side effects, or 1 have a side effect, or 2 have a side effect. Okay, so let's work it out. Probability of none, we already have some of these. 1 minus, what's the probability of none? Well, that's up here, 0.3584. What's the probability of 1 having a side effect? 0.3774. So I'm going to add those. And now what I've got to do is work out, well, what's the probability of 2 having side effects? So that's 20 C2. Probability of success, in other words, probability of side effect raised to the power of 2, 0.95 raised to the power of 18, and that becomes, now 20 C2 is 190, because it's 20 times 19 of 1 by 2, which is 190. times 0.05 squared, which is 1 over 400, which comes out as 0.0025, and then 0.95 raised to the power of 18, and that comes out as 0.3972. Okay, so let's multiply those. Multiplied by 0.0025, multiplied by 190, and that comes out as 0.1887. Okay, so that goes in here, 0.1887. Now, 0.1887, so we've got to add these three together now, plus 0.3774 plus 0.3584 is 1 minus 0.9245. Sorry, 44845. Yeah. So 1 minus that, and the answer comes out as 0.075. Now, I hope you remember that they're asking for percentages. What's 8%? 8% is 0.08. This is less than 0.08, so therefore the claim is true. 0.075 is less than 0.08, so their claim is true. Okay, so that's a straightforward, 3 examples on a straightforward usage of what we would call the Bernoulli trial formula or the binomial distribution formula. Now, one little spin on this, and I'm going to do a couple of examples on this, is where they ask you to put a condition on maybe the last outcome. Something like this, for example. A coin is flipped repeatedly until 10 heads appear. Find the probability that this will take exactly 17 flips. Now, notice that you're being told what you have to end on. Okay, so on the 17th flip, what are we told? It has to be heads, and it has to be the 10th head. See that? So it says there, a coin is flipped repeatedly until 10 heads appear. So just keep tossing the coin till you get 10 heads. They want to find out what the probability is that it will take exactly 17 flips. So in other words, on the 17th flip, you get the 10th heads on your coin. Okay. Now, what does that mean? If the 17th flip is the 10th head, then there are 16 flips. 16 flips, can't even spell now at this stage, so take that out there. There are 16 flips in which I have to get 9 heads. See that? And that is where I'm going to bring in my Bernoulli trial. So the last one is already set for you. The 10th head has to be on the 17th time. So therefore 9 heads have to occur during the first 16 flips. Now, is this a Bernoulli trial? Yes. Why? Is there 2 outcomes? Yeah, heads or tails. What's the probability of heads and what's the probability of tails? Well, it's a half each because it's a coin and it's a fair coin. All right. Okay, how many times are we going to repeat this? N is 16 and the number of successes I want will be 9. So therefore 16, out of the 16 turns I want to get 9 successes. The probability of success is a half and I want 9 of them, so therefore the probability of failure is a half and I want to get 7 of those. So that's going to represent the probability of getting 9 heads in the first 16 times. So 16C9, which is exactly the same as 16C7, not much of a difference. I'll go and work it out in the calculator. 16C9 works out as 11,440. Okay, multiplied by 0.5 raised to the power of 9, which is 1 over 512, multiplied by 0.5 raised to the power of 7, which is 1 over 128. And when I multiply those, 512, and multiply that by 11,440, we get an answer of, in decimal form, 0.17456, so 46, just to round it off to 4 decimal places. Okay, now that's the probability of getting 9 heads in 16 flips, but I want to have a 10th head on the 17th flip. So that and the probability of getting a 10th head on the 17th flip, which is obviously a half, because that's definite. Probability here of a heads is most definitely a half. So you bring that down and you multiply it, and when we multiply that by 0.5, we get a probability of 0.0873. And that's it. Okay, now I've gone through that with you, and again, I have printed this one out, I hope, in order for you to be able to see it carefully. 10th head must appear in the 17th flip, so the other 9 can be in the first 16. Okay, that means n is 16, the probability of success and failure are half each, and r is 9. So therefore 0.0873 is the answer when we take, as you see it here, there's the probability. That there represents the probability of getting 9 heads out of 16 turns. You then multiply that by the probability of getting a head on the 10th turn, which is a half, to get an answer of 0.0873. Okay, let me just take 3 examples involving this kind of thing. Okay, when a thumbtack is thrown on the floor, the probability that it lands pin up is 1 over 5. The thumbtack is thrown repeatedly onto the floor until it lands pin up for the 3rd time. Find the probability that this will take exactly 10 throws. Now, first of all, let's establish here that it is on the 10th throw that I want the 3rd pins up. Okay, so that's what we've got to remember. So on the 10th throw, what do I want? I want the 3rd pin up. Okay, now first of all, we've already established this is a Bernoulli trial. There are only 2 outcomes. There is a pin up and there is a pin down. Okay, the probability of a pin up is a 5th, so therefore the probability of pin down is 4 over 5. Okay, now find the probability that this will take 10 throws. What will take 10 throws? The pin up for the 3rd time. So therefore pin up is going to be my success criteria. So P is equal to a 5th and Q is 4 over 5. Just to give them the proper notation, P is always the probability of success, Q is always the probability of failure. So what do we want to do? If the 3rd pin up has to occur in the 10th throw, then there will be 9 throws in which I want to get 2 pin ups. Okay, so therefore 9C2, because the pin up is my success, probability of success is a 5th, raised to the power of 2. The probability of failure is 4 over 5 raised to the power of 7. So if we work that out, 9C2, that's 36, multiplied by a 5th, 0.2, raised to the power of 2, which is 1 over 25, which is 0.04, multiplied by 4/5 raised to the power of 7. So a lot of the work involved here is simply calculated work, which takes a while. So that's 0.2097. Okay, so when I multiply those out, I end up getting 0.3019, so 302. So that's the probability of getting 2 pin-ups in 9 throws. And I want the 10th throw to be a pin-up. So on the 10th throw, we want a pin-up. And the probability of a pin-up, we already know, is equal to a 5th. So you multiply that then by a 5th, because the first 9 throws I want 2 pin-ups, and I want the final throw to be a pin-up. So when I multiply that by 1 over 5, as the calculator will tell me, I get an answer of 0.0604. And that's the probability that it'll take 10 throws to give 3 pin-ups. Okay? Next one. A woman phones householders randomly. Wouldn't do that, that's not good, you could be arrested for that. But anyway, a woman phones householders randomly. She finds that only 20% of householders reply to her questions. She decides to keep ringing until she gets 4 householders who reply to her questions. Find the probability that this will take 10 calls. Now, First of all, this is a Bernoulli trial. There's only two outcomes. They answer or they don't answer. So they'll answer or they don't answer. Okay, they're the only two outcomes we have. Now, what's the probability of an answer? The probability of answering, it says here, 20%, and 20%, 0.2. So therefore, the probability of not answering is 0.8, because they both have to add up to 1. What's going to be my success criteria? Well, she keeps ringing until she gets 4 householders who reply. So therefore, answering is going to be success. So P is 0.2 and Q is 0.8. How many times? Well, it says that she's going to keep ringing until she gets 4 householders who reply to her questions. Find the probability that this will take 10 calls. Now, on the 10th call, what do I want? I want my 4th answer. See that? So on the 10th call, I want my 4th answer. And that means the probability of getting an answer on your 10th call is going to be 0.2. So let's keep that in mind. What does that mean? That in the other 9 calls, what do I want? I want 3 answers. So there we have it. Here's where you're going to use your Bernoulli trial, because 9 will be N, 3 will be R, P will be 0.2, and Q will be 0.8. So we use 9C3, because that's the number of successes I want out of the 9 first calls, by the number of successes, by the probability of success, I should say. Let's just get rid of that. By the probability of success, which is 0.2 raised to the power of 3, by the probability of failure, 0.8 raised to the power of 3, that's 6. Okay, so 9C3 is 84, multiplied by 0.2 raised to the power of 3 is, in decimal form please, 0.008, and 0.8 raised to the power of 6 is equal to 0.2621. Okay, so this is going to represent the probability that in the first 9 calls I get 3 answers. All right, so 84 multiplied by 0.008 multiplied by 2621 comes out as 0.1762. But that's only the probability of getting 3 answers in 9 calls. We have to remember that we want an answer on the 10th call. So it's this and an answer, which is 0.2 on the 10th call. So when you multiply that by 0.2, the overall probability drops to 0.03523. And that's it. Okay, so again, you just have to be careful that if there's something happening on the last attempt or the last trial, that you mark that down first and then see how many trials beforehand occur and how many successes you want out of the previous events or previous trials. Okay. Last one. How many times must a fair coin be flipped in order to ensure that there is at least a 99% chance of getting at least one tail? Now, there are 2 things in here that we have to watch carefully. At least 99%, at least one tail. And I told you before, when you get questions that involve the words at least, you turn them round on themselves and you state the opposite. Okay, so if there is at least a 99% chance of getting at least one tail, doesn't that mean that there is less than a 1% chance of getting no tails? So just think about that. If there's at least a 99% chance of getting one, then there must be less than the remaining 1% of getting none. And that's far more easy to calculate. Okay. Now in this case, notice what it's asking you. How many times? So this is a question where we've got to calculate the value of n. So first of all, write down for, well, is it a Bernoulli? Yes. Why? You're flipping a coin. There's only 2 outcomes. So you have NCR by the successes, which is the probability P to the power of R, and Q, which is the failures, raised to the power of n minus R. That's the formula. So it's n we're going to be looking for here. Okay. So in this case, it'll be no tails and less than 1% chance. So out of the number of events, I want no successes. See that? By, what's the probability? Well, it's obviously 0.5 because it's a coin. So the probability of success is 0.5, probability of failure is 0.5, and that's raised to the power of 0 by 0.5 raised to the power of n. And that's going to be less than 0.01, which is the 1%. Now listen to that again. At least 99% chance of getting at least one tail. Turn that around on itself. Less than a 1% chance of getting no tails. So no tails. First of all, we need the probability of heads is a half. Probability of tails is a half. What else? Heads is going to be my success. That's a half. And Q is also going to be a half. Okay. So in this case, we want to find out no tails. So out of that number of goals, which you're trying to find n, I want no successes, multiplied by the probability of success raised to the number of successes, multiplied by the probability of failure raised to the number of failures. So this becomes nothing more than 0.5 to the n is less than 0.01. Go back to logs. If I want to get rid of this base here, log to the base 0.5 of 0.5 to the n, log to the 0.5 of 0.01. So in this case now, they'll cancel n, and you're going to switch your sign, because don't forget log to the base 5 will be negative, so therefore we're divided by a negative, so the sign switches over. And just to work out in your calculator, 0.5 of 0.01, and that comes out as 6.64. Now, what's the first natural number greater than 6.64? N must be equal to 7. So therefore, the coin must be flipped 7 times in order to ensure that there is at least a 99% chance of getting at least one tails. Okay. I'm going to leave you with some questions to do. I'm going to leave you with pages 92, 93, 94, 95 and the questions that are there. All you're doing is listening for, first of all, using a formula Bernoulli trial, but you're listening for the words and the word or. And you know that and is multiply, or is add, and simply use the Bernoulli formula, or what we call the binomial distribution formula, to work out the probabilities of the given successes and failures that you're asked about in each question. If you need any help with these, you know where I am.